Hello, I was actually ready to do the next video on the code, phase 3, but when I was sort of going through the content of the code and looking at what I was going to describe it suddenly occurred to me that actually really we probably could do with a quick video on bitwise manipulation in C, and how C deals with all those various bitwise operations. Because if you think about it, bitwise operations are how microprocessors make decisions and check flags and set status flags and all sorts of stuff. So within the emulator, not only does the emulator itself actually use these bitwise manipulations, but the microprocessor itself does as well. So with that in mind, I resurrected an old slide, and this is all of the bitwise logical manipulation that we're going to need. The not, not just flips the bits. So if you take this binary representation, this binary pattern here that we've got in our A variable or A register, or how we're going to describe it, not would take all the bits and turn them up to the opposite. So in this case, it would turn it into 0 1 0 1 0 1 0 1. Now, there's a really nice freeware calculator called Calculator, and if you turn Calculator into scientific mode, it also gives you the option for playing about with various bases and stuff over here. So if we take, I'll tell you what, we'll do it in hex because we know what the thing is. This is a representation in hex of AA. So if we look at that AA and then turn it into binary, you'll see that it is exactly what we got there. Now this, when you flip it over, that is the binary representation of 5 5, and what you'll note is in electronics in particular, but also in computing, AA and 5 5, these two patterns are used quite regularly because they allow you to see quite clearly the settings of a memory address. You set it to AA and then you set the next one to 5 5, and it allows, they use it in memory tests and all sorts of things. But that's what not does. It just turns the bits around. The logical OR, well, what logical OR does in this case is an A ORed with B, so the contents, this binary contents of A, logically ORed with the binary contents of B. And binary OR says if one or the other or both are set, then the result is set. So if we go through this, one or one, well, one or the other or both, so the result is yes. One or the other or both, so neither, so the answer is no. One or the other or both, well, there is one set, so the answer is yes, and the answer to that next one is no. Then you've got yes, 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 and no. Okay, so a logical OR is used to set a specific bit. As you can see there, we've set bit 3 to something different. So A started off as 10 10 10 10, and bit 3 is now set. So that's how you would, within C code, within any code actually, that's how you would set a bit. The Xor function is different to the OR. Obviously it's a different function, but what does that do? Well, the exclusive OR says one or the other, but not both. So in this instance you get 0 0 1 0 0 1 1 0. Okay, and the exclusive OR is used to flip a bit. So you can actually take a bit from what it was to something new, because if you exclusive OR it with a 1, well, if it was a 1 originally, then it will turn into a 0, and if it was a 0 originally, it will turn into a 1. The AND function says both have to be a 1 for the result to be set. So you have, in this instance again, 1 0 0 0 1 0 0 0, because you can follow that down. both have to be a 1 for the result to be set. Now, ANDs are used to check bits. We'll come on to that in a little while. There's a piece at the bottom here shows how that works, but that's the logical AND sometimes along with the shift, but you can use a logical AND on its own to check a bit. The NAND, well, this is effectively a not AND. So what you can do is you can use the not function and the AND function together to check, to set the result. And so in reality then, you take the AND and you not what's in the AND, you end up with 0 1 1 1 0 1 1 1. And the not AND is actually used effectively to clear a bit. So it says if something is we'll see it in action later on, but this is how you do it. You would clear a bit using the NAND function. The little chevron things there, you can actually, this is a logical shift right. You can use a logical shift left by turning them little chevron things the other way around, but just for want of demonstration. And what that says is move whatever's in A right by 5 bits. So 5 bits disappear. 1, 2, 3, 4 and 5, they all disappear, and what you're left with is 1 0 1. But what the shift right does is it actually, for every bit you move it puts a leading 0 in, so you end up with 5 leading zeros. 1 0 1. And if you were to logically shift left, then you would end up moving it the other way and the zeros would come in on the right. So in C, you represent the not like this. A equals not A, so that's pretty straightforward. Flip the bits. This is an OR, so A equals A or B, but this is the shorthand way of writing it. It's the most common way you'll see it, which is just a way of saying OR A with B. This is the exclusive OR. The little hat symbol there is the exclusive OR. This is the AND. Now this one is how we described it before, the not AND. So in the parentheses, the parens here, they make the A and B a higher priority, and therefore A and B gets done first, followed by the not, as we can see there, that's the not. So so that will give you your NAND function. Now this one, these two, believe it or not, are equivalent. So what this says, well actually it's not quite equivalent because I haven't put the if statement in, but the actual formula is equivalent. So you've got A shifted right by 7 ANDed with 1. So that's testing bit 8. So you shift it right by 7. 1, 2, 3, 4, 5, 6, 7. They all disappear. So from there to here disappears, leaving you with the 1. And then you test it with the number 1, because this number 1 would be on the right hand side here now because you shifted it right by 7 bits. And if you tested it with a 1, remember A and B, for AND to work they both have to be a 1, so that says if the result is true, then that bit must be set. If the result is false, then that bit is not set, so therefore that's how you check a bit. Now this bit is exactly the same thing, because 128 in binary is represented like that. So what you're saying is mask out all of these bits, because remember A and B, so the only one that can be true is this one. So for the result of that to be true, A and 128, that bit must be set. If it's false, that bit isn't set. So bit 8 is tested there. Now if you wanted to test 2 bits, you could easily test this bit and say this bit here at the second position, there's a 1, there's your 2's position, and you would test that in your 2's position by changing that to 130 like that. And this is called bit masking, but it's basically how you check if a bit is set within your within your register or within your memory location. Okay, so this is my basic overview. It's something I used to remember how it was all done and what you used each of these individual bitwise manipulation functions for. So I'm hoping that one's quite useful, and certainly it will be a good explanation for why we do certain routines within the emulator going forward.